My name is Alex Bantis. I'm a back-end Scala developer at Tubi. Tubi is this place where people go to watch movies for free. I've been working over the past 18 months on personalization services. And in a nutshell, my presentation is about this. I think Scala is awesome. I think ScyllaDB is awesome. And when you put them together, you get awesome squared. So before I get started, the first thing I just, at a high level, I want you to understand is I think ScyllaDB is awesome. I'm a back-end developer. I've been working at Scala in several years, and I think Scala is awesome. And what I've learned over the past year is that Scylla plus Scala together is awesome squared. And so if you take away anything from this talk, it should be to go out and use Scylla and go out and use Scala and use them together. First, a little bit about Tubi. What is Tubi? It's a place where you can go to watch movies for free. No credit card, no sign up, no subscription. We've been growing pretty fast. And a lot of numbers, a lot of these are out of date. The most important one you want to focus in for this session is 15,000 titles. We got a lot of movies. What you see right here is our home screen. So when you enter into the Tubi experience, you want to pick a movie you like, and you can either scroll down or scroll right. And what's really important is to find the movie that you really want to watch. So our mission is to make Tubi into a data-driven organization. And I'm going to talk today about two projects, Scala projects, by the way, that have been really transformative in that, and just talk about some of the lessons we've learned and some insights you might be able to get from that. Our mission depends upon people being able to find the movie that they like. A study by Netflix has shown that people will spend about a minute trying to find the movie they like before they give up. So this is where personalization comes in. What we want to do is find the movies we think the user is going to want, and we want to shift them left and up so that they can find the movie that they're going to be really happy with. So the problem, this is when I came to Tubi 18 months ago, this is kind of what our stack looked like for this part of our service. The homepage service, let's see if I can get this to work. The homepage service at the bottom is a back-end Node.js application. This receives requests for the homepage. It's a monolith Node.js application, and it does a lot of stuff. One aspect is personalization. So the little guy at the top, he's the one who's designing the ML experiments to try to find the perfectly best algorithm to use. So he's going to run A/B experiments to find the best algorithm. So what is he going to do? He's going to, first of all, create the ML model in Spark. And then he's going to write the data to Redis. Redis is kind of this source of data for the application, and it's also a data exchange format. And so he's got to update the code in the homepage application. So, and he doesn't actually do it because he isn't a back-end engineer. So he's got to work with that team and get those code changes made and pushed into production. And then when the experiment's actually going to start running, then he's got to update the configuration of the experiment engine and get this to be pushed into production and restart. When the experiment ends, he's got to do the same thing to stop the experiment. And he doesn't own Experiment Engine. This is another Node.js application that's owned by back-end devs. So it's time to upgrade. there's a lot of different reasons you could upgrade. A lot of these decisions that were made at when Tubi was a small little startup probably made a lot of sense at that time, but now Tubi's bigger, better, stronger, faster. Maybe we should revisit some of these things. So these are all the kind of usual suspects that you would have for doing an upgrade. So in the course of making things better, we actually did accomplish a lot of these things. At the time that I came, it took about 300 milliseconds in order to deliver a personalization of the home screen, and we got that down to about 10 milliseconds for the P95. It became much more stable, the code became much more maintainable, we had better fault tolerance, but that wasn't actually the problem that we were trying to solve. The problem was a people problem. So every time that the ML engineer had to run an experiment, he had to say, please, this other team, please make these code changes. And so it was an endless cycle of please and I'll get right on it. And this is kind of what it looked like, right? So every time there was a code change, that begat a PR and a PR review and unit tests and deployment to staging and on and on and on. So it was a very, very heavyweight process to conduct experiments. So our solution, so we have the new way of running experiments. So in this new way, so first of all, everything having to do with personalization was extracted out into this new application called Ranking Service. And we rewrote the experiment engine as Popper engine. So both of these are Scala, Akka applications. So the new way of doing things, the ML engineer, he creates the model in Spark, and automatically it gets published to the application via Kinesis. Doesn't have to do anything. So all he has to do is create his model and make it run, and there's an Airflow job that just automatically publishes it to Ranking Service. He's got to go into the UI and schedule an experiment to run in the future. And when the appointed date arrives, it just starts running. And when the experiment finishes, it just ends. And that's it. So he doesn't need to talk to anybody. We don't have to have any code changes, PRs, unit tests, deployment to staging. It just works. And the basic flow is that the home page service will make a call to Ranking Service. Ranking Service will then make a call to Popper engine and say, okay, is this under experiment? Which way do I go? Do I do the A or do I do the B in the AB experiment? Or maybe it's not under AB experiment. And then an event is published to analytics. So everybody's happy. They don't have to talk to each other. Well, of course, until the next thing comes up. So there's a lot of things that contributed to the success of this whole thing. Testing tools. We had really good testing tools. Scala and Akka, just an awesome combination. gRPC and protobufs. AWS, plus much, much more, and of course, ScyllaDB. And I could talk about all these things. I could talk and talk and talk, but I don't have time. So I'm just going to focus in on three things. The first thing I'm going to talk about is on data and domain modeling. So in case you don't know, Scala is built on top of the JVM, and it's just this really great venue for expressing what you want to express in terms of a data domain model. Facebook, back in the early days, used to say that we need to move fast and break things. And interestingly, they don't say that anymore. What they say is, move fast with a stable infrastructure. And so when you're a startup, you have to go fast, but you also have to go slow in some ways. And the question is, well, where do you go fast and where do you go slow? And I would argue that a good place to slow down is in your data model. Because the data, for those of you who build microservices, the data is your reality. It is your source of truth. And so it's worth taking a moment to slow down and get it right. So we're going to take a look at a little bit of the domain model for ranking service. And as I said, getting it right is not easy, but as I hope you'll see, the payoff is pretty big. So this is the foundation of the data model. An ID is basically the atomic unit of ranking service. And a ranking, just to be clear, is the pre-computed output of applying an ML model. So if I have an ML model and I apply it to me, based upon my viewing history, I end up with a list of videos that the algorithm thinks I'm going to like, and that list of videos is my ranking. So ID is the foundation of everything, and a target is simply a non-empty list of ID. So a target could be me when I'm at home watching on my OTT big screen. A target could be all iOS users in 90210 in Beverly Hills. So ID can be a lot of, target can be a lot of different things. Oops. OK, so ranking is simply data, metadata, and a target. And so data is simply that ordered list of IDs. And what's really important here is, to get this to work, is the model state. So the model state expresses the idea of whether this ranking is in a release or whether it exists for the purpose of experimentation. So the really important part here is that experimentation is a first-class citizen of the data model. So whenever I want to run experiments, I don't have to do any code changes. So with this kind of data model in place, then this is what the gRPC protobuf message looks like. This is what the Scala code looks like. And this is what the ScyllaDB schema and the table looks like. So once we actually have this kind of data model in place, everything from that kind of flows together. And one of the impacts of this is that I leverage the type system in Scala. So if I need to make some sort of code change and I'm going to add a new type of ML application, the compiler is just going to let me know what I need to do, basically. So it's very low cost in order to upgrade and make this more extensible. So the next thing that I want to talk about is Scala and Akka. So we're going to look at Popper Engine this time. And concurrency is super hard. People who work as back-end engineers, if they're very lucky, they don't have to think about concurrency because it is really hard. Thinking about concurrency is like trying to think about distributed systems. Everybody here who's using ScyllaDB works with distributed systems. But you don't have to think about it because ScyllaDB has kind of abstracted that out for you. Scala provides some nice abstractions over Java concurrency, which is not very pleasant to deal with. But even with those concurrency, even with those concurrency abstractions, it's really hard. But the good news is you don't panic, right? Because there's this thing called Erlang. If you haven't heard of it, I'm sure you've used it because 90% of the switches on the internet are powered by Erlang. WhatsApp is powered by Erlang. Akka is basically a JVM port of Erlang onto the JVM. And so using that allows me to program in a way where I don't have to think about concurrency. Just like when I use ScyllaDB, I don't have to think about distributed systems. So we're going to take a look at this concept of namespace in Popper Engine. And a namespace is kind of this space where you could run experiments. And OK, so a namespace has state. Oh. My God. My God. Oh. Sorry. Sorry. Let me be careful. OK. So namespace has state. We have experiments that are running and going to be scheduled. And we have this concept called segments, right? Because if I have an experiment running, the experiment has an ownership over a certain segment of that namespace. So if I'm going to run an experiment and I say, I want this, I want, say, 20% of traffic coming into Tubi to be part of this experiment, then we have like 20% of the segments in the namespace that are going to be allocated there. And this is kind of what a very simple implementation of namespace looks like. Now, the issue here is that it has state. It has mutable state. And mutable state in a concurrent world is very complicated. The way that you would solve this with Java is you would obtain a lock. And so you'd have multiple threads that would be in a queue waiting to be able to access the state. And that's eating up CPU. So Scala, by the way, is not a functional programming language. It is actually a polyglot It is actually a polyglot language. So you can do many things with it. You can do object-oriented. You can do functional. You can do actor model. You can do all these things. But the trick is that if you try to put all of these together, you end up with spaghetti. It's a mess. It's difficult to reason about, difficult to think about, difficult to refactor. So the strategy here is to break things up into separate spaces. So everything having to do with object-oriented stuff, object-oriented design patterns in Java, by the way, they're really cool. And I use them, and they help me to solve problems. So this is where the object-oriented design patterns come in. I have this object with state and methods to operate on the state. We have functions. We put everything having to do with functions in this separate space. And then we have this thing called an actor context, where I can pretend that all of my code is running in a single thread. So from this, right, Akka and Scala is very powerful. But one of the things you want to do is keep these different paradigms in different spaces. And that'll make your life really simple. You want to leverage the type system, right? Scala is really great for modeling a domain. And this is exactly what you want to use it for. You want to understand the JVM, because even though you have this idea of immutability first, you have to work within the constraints of the virtual machine and the garbage collector. And sometimes you need to drop down into a more primitive level. And finally, you can do lots of things with Scala. It gives you great freedom, but just because you can do everything doesn't mean you should. You should impose some sort of discipline upon the kind of constraints that you have. So the next thing I want to talk about is Scylla, and I'm going to go through this very quickly. We're basically, like, these are the specs we've been running in EC2. I think you guys already know how they're different, how it's the same as Cassandra. This is the performance improvements we got when we switched to the shard-aware driver. But it's way more simple. So we're just building up an infrastructure team right now, but I didn't have an infrastructure team when I started it. I know how to do JVM tuning, but I don't want to spend my time doing this. I want to spend my time building applications. So ScyllaDB has been very helpful in that aspect. And it's way faster than Cassandra. So we have these bursts of writes, and even when we have these bursts of writes, you have hardly any impact on the reads. So it's super fast. So in terms of tips that I've found very, very important, the first one is own your own data. Very, very important. Take the time to really think about it. It's a source of truth, and it guides all of your business logic. Build your data model in harmony with the database. This is very, very important. Build for blue-green deployments. Changes in the schema have been super simple, simply because of the way that I've designed everything. You notice the API and the input nodes have been decoupled. Kinesis, the data in Kinesis has a TTL of 7 days. All the data that I write into ScyllaDB has a TTL of 7 days. So what's in ScyllaDB is basically a mirror of what's in Kinesis. If I want to do an upgrade, all I have to do is spin up a new cluster and read from it, seed it in, and when that's done in maybe an hour, I just take the API nodes and repoint them to the new cluster and kill the old one. So you want to try to decouple reads from writes. Use Kafka and Kinesis when you can. And then finally, compression is super important. So that same protobuf message that we define as the API in terms of publishing from Spark and Airflow, we use that same mechanism to save to the database. So the result is we have, it's super fast because we have a very efficient compression mechanism. And so in conclusion, just this combination of Scala, Akka, and ScyllaDB is just awesome squared. And I hope you guys all go out and use it.